Okay, let's continue the second part of the radiation transitions. So, this is today's outline. I think the major goal is to introduce two important concepts. Yeah, we can call it still in the solid-state physics, but it is a little bit too deep for a course just called solid-state physics. We call it momentum matrix and the transition matrix. And surely in order to derive the form of the transition matrix, we need to start with some term called the Fermi-Golden rule. But Fermi-Golden rule is also a very deep concept. Usually is in the second quarter or second semester of the quantum mechanics. So we will directly use the result. We're not going to derive that. I need to mention that in order to derive the momentum matrix element and the transition matrix element. Then we can finally tell you what the radial transition rate looks like and how to influence the transition rate in the solid. Okay, and this is what we learned from the last lecture. So in the radial transition, we did three of them. The fundamental radial transitions. The one is stimulated absorption, stimulated emission, and the spontaneous emission. And next week we said that actually stimulated absorption or absorption and the stimulated emission, they are actually one process. They are not two processes. They are just the same process in the direct or reverse direction. And the other spontaneous emission is also not independent. It's correlated to the absorption process. So there should be 1.5 radiation transition only. Since we proved according to Einstein's AE coefficient methodology that their coefficients are all correlated. First is B12 is to B21. So that proves these two are the same transition. The second is the spontaneous transition coefficient A21 can be times the original B21 with its corresponding density of state in the density of optical mode, the density of optical mode in the solid, then times the energy of the photon itself. Okay, so as long as we know what a B12 is, then we know everything. But so today's progress is know what the B12 or B21 looks like. So in order to answer this difficult question, we need to return back to the solid-state physics again. That something important called Bloch theorem. Bloch theorem stated that this is the Hamiltonian of the time differential equation. H bar is equal to minus H bar squared times Laplacian divided by 2m0 plus its potential then is equal to E phi. It's an eigenvalue problem. Then Bloch theorem stated that if the potential VR is periodic, that means B of R plus a translation vector will be identical to itself. Then the answer phi must be expressed form like this. It could be a solution with a plane wave times a central function, which is also periodic to the lattice itself. Okay, so that's a great achievement. So, not achievement yet. It's a great important step forward. So if we put this form back to the original Hamiltonian, and after some rearrangement, we will see the Hamiltonian looks like this. It's a form of k, a function of k. That means the Hamiltonian when k is equal to 0, and the k is equal to Edward pi or another number, will be different. Because it turns out that if we put the Laplacian to be ikr, it will drop ik out. So the Laplacian itself becomes a function of k. Yeah, then you have so under such circumstances, the solution with different k surely will give you different U of k of r. Then with this kind of different UFK, surely you will have a different energy, corresponding energy. So if you plot all the energy with different K, one by one, that gives the plane structure of the solid E of V of K. Then what we are interested in is that what a UK looks like. The central function in function of K should be looks like. Actually, it's not important to know what it looks like. What is more important to know is symmetry. As long as you know the symmetry, how the symmetry should be, that will be enough for the class today. Alright, so let's see. So, because U of I is also a mixture of the original wave function of an atom. So, for example, for the conduction band, U of I is also some kind of transform from the s orbital. We call the conduction band, and it has the lowest unoccupied state. And the band in the valence band, usually noted as UV, is the combination of 3p orbital. So 3p orbital in, 3p 3 valence subband out. So that gives us the heavy hole, light hole, and the speed of hole. Then we also need to remember that the symmetry of the UR, the conduction band wave function, will be pretty light. Not totally the same, because it's already a mixture of or have some interaction with the crystal potential. So now it's not totally the same, but looks like. Okay, and this is enough. And the second, the symmetry of UR for the valence band also should have the similar symmetry with its p orbital. Then that also decides why the symmetry of heavy hole, light hole, and the speed of hole. Then because the UC and the UV have a very strong resemblance probably not. They are pretty alike. So there's also an important property will follow. For atomic orbital, that the different orbitals are all orthogonal. 6 the same for the central state, central function derived from them. So the UI bracket Uj is equal to delta Ij. That means if you integrate all space I and Ui star Uj R squared to all space will be 1 if I is equal to j, will be 0 if I is not equal to j. Yeah, this is the definition of orthogonal. So we have a simple way to write it down to go down. This is delta Ij, the delta function, Kronecker delta function. Okay, so let's start with the symmetry of UC. To discuss the symmetry of UC, let's start with the symmetry of the s orbital. For the s orbital, the function is purely radial. The wave function is invariant from any angle. That means usually we think that the phi of ns should be 3 parameter distance theta and phi according to the spheral coordinate shown here. But for the s orbital, it is not a function of theta and phi. It's only a function of r. It's only a radial function. So that will give you that if r is equal to 0, this function will be a constant. And for UC, because you are in the lattice is no more symmetrical invariant. But the lattice has an inversion symmetry because it is translational. That means if you see the wave function from R and from minus R, it should be the same. Yeah. So you have the even symmetry to the origin. The even symmetry, that means this is the even function. If you put the equation with R, and then the other, and that will be the same as if you put the equation with minus R. Okay, this is the one important property of the conduction band orbitals. Second, this is the wave function of the p orbitals in the atom. So the p orbital with different orbital number, quantum number n and p, will be decoupled into one radial function and one angular function. Looks like that. And since it is p orbital, so the angular momentum, the quantum number of angular momentum L is equal to 1. Yeah, I hope you have some memory about what you learned in the modern physics or quantum physics. If it is not, probably just Google it. You don't need to go into deep. This is everything you need to know. Alright. And if you pull out the wave equation of Px, Py, and the Pz, it looks like this. The Px is A times sine theta cosine phi. And if you do some definition of x, y, z to the r theta phi, you will see that sine theta cosine phi is actually equal to x divided by its distance r. So that's the reason we call it px orbital. That is this wave function is actually more a function of x only. Second, similarly, we have the phi py is equal to sine phi, sine theta sine phi, and it's a constant times y divided by r. Third is a function of z. Okay, so you have px, py, pz. And you see these three functions, they are arc symmetry or arc function to the origin. If you pick any x, for this case, if you put x into the minus x, you will get a number to the negative 1. So it's an arc symmetry. So the orbital looks like this. For the px orbitals, is a function along the x direction. If one side is noted minus, then the other side will be noted plus. That's just the value you will get according to the wave function. And so does py. You have a plus in the one side of the y-axis and the other side of the minus axis. And the z, one is plus and one is minus. Okay, so we have an important thing to know. The valence band, the central function of the valence band, shares the same symmetry with the p orbital when it comes to the inversion symmetry. That the uvx minus x will be uvx minus okay. Oh yeah, there's a minus here. So if you put a minus in, you will just let one minus out. Yeah, so the symmetry is like this. Then with these two terms, we can start to derive some properties in the wave functions. And before doing the mathematics, we also take a review of a quick mathematics. So what's the best property while we are dealing with even and odd functions? Is that we can determine the integral to be 0 without knowing what it is. If another function is called f is equal to g times h, and the g is even function, h is even function, and f is also even function, 正正得正, something like that. And if g is r, h is r, then it's an even function. And if one of them is even, one of them is r, then the multiplication will be an odd function. Okay, so that's the operation of the multiplication between even and the odd function. So in some terms, we will call it the even parity or odd parity. That's another word to describe the symmetry. Although I doesn't really know why they use the two different words, but they at least to here they are the same statement: even parity or even symmetry. Okay, so if the function is odd, the best the best property is that all the symmetry integral, or we can call it the Cauchy principal integral, from minus a to a will be 0 because you have plus here and minus here. So after something in that will be 0. So that will be an integral of 0 from here to somewhere. So even I don't know what is antiderivative, and I also don't know what is sign. This property already tell you a lot of things. Its integral over space will be 0. Okay. So if it is the second, the rule of differential. If you take a differential of even symmetry, that will give you asymmetry. Okay, so if d over u of minus x over dx will be minus du of x over dx, that is for sure. If u of minus x is equal to u of x, then wait a moment. Okay. So let the x plot is equal to minus x dx plot will equal to minus dx plot. So it should be du over x plot over minus du over dx plot. This should be more correct. So if it is an even function, that means this term will be equal to its original one. So that will be minus du of x over dx even part. So after derivation of an even function, this is the definition of the odd function. So this is f of plus minus x, and this is f of plus x. So going to odd. Alright. So an even function, take a differential will go to odd function. Similarly, if you take an odd function, okay, so I can choose another. If it is an odd function, that means this is going to be minus plus du over x over x. Yes. This is for odd function, original odd function. Then this is the f of plus x, and this is the f of plus minus x. So in this case, it becomes even. Alright. So the one simple differential will change the parity of the even or the odd function. Taking one differential odd to even, and the second differential, for example, Laplacian, that will go back to 0 even again. Okay, I already proved that, so it's already already here. It's empty. Yeah, okay. Since that I have. Okay, let's take a quick stop. You can try to write it down more in full stage. We will return.